Welcome all to Agilent USB 3.0 webinar. Today we will hear a presentation by Jim Chu, he's Agilent USB Technical Lead, and by Don Schoenecker, he's Agilent USB Protocol Validation Lead. In addition, also online is myself. My name is Yoram Shimoni. I'm responsible for Agilent Digital Business Development in the EMEA. This is a lecture-style meeting, but you can send questions in writing using the Q&A functionality in the WebEx meeting console. You should see it in the lower right hand. We will keep your identity private when you're asking questions, so we just answer the questions. Thank you all for joining, and Jim, you can start. Please take the lead.
Thank you, Yoram. Hi, my name is Jim Choate. I'm the USB Product Manager at Agilent Technologies for high-performance oscilloscopes. Today we'll be presenting USB 3.0 product development, technology overview and testing, and the challenges associated with certifying your products. I'll start the presentation focused on physical layer test tools, and then turn it over to Don Schoenecker for the protocol and logic analysis portions. And then we'll follow it up with a summary and then a Q&A session. So I joined Agilent in 2007 as a high-performance oscilloscope product manager. I worked prior to that for Intel for 10 years, starting in motherboard design and validation, and also on the Serial Standards Initiative team, working on the USB 2.0 specification, 3.0 spec, USB compliance program, where I served as a compliance committee chairman from 2003 to 2007, and continue my close engagement with the USB-IF as a technical lead for physical layer validation and testing of USB 3.0. So here's our agenda. We have a lot of material to cover, and I apologize for giving you so much information, but USB 3 has been rapidly deploying, and there's a lot of information required to understand what is USB 3.0 and what are the requirements for physical layer and protocol layer testing to achieve certification and be confident your products meet the specification and will perform well in the field. We'll start out talking about the Agilent Digital Standards Program, and then I will give you an update on the USB-IF compliance program status and certification of USB 3.0. Then I will go to discuss physical layer testing, transmitter testing, receive testing, and cable connector testing. And then I will discuss the physical layer compliance test pitfalls. This is a list of most commonly failed parameters at compliance workshops and test labs that give people a lot of problems when they try to go for certification and to verify their designs. Then I will transition and turn it over to Don Schoenecker. He's the product manager for the logic side, so he will discuss the protocol analyzer and jammer technologies used to debug and test the software, firmware, and protocol layers of USB 3.0 solutions. Then we'll conclude with a summary and open it up for questions. So I mentioned Agilent Digital Standards Program. This is the standardized method that we use within Agilent to address the needs of adopters of different serial standards. So we engage at the highest levels of the different standards committees. As you're probably aware, there are many, many different compliance and standards organizations that drive the technologies for different areas of consumer and different electronics. We participate on the boards and compliance workshops for many standards driven by JADEC, the memory organization, PCI Express, where we have one Agilent representative sitting on the board of directors, Serial ATA, DisplayPort, HDMI, the display standards, USB Technologies, which is my realm, and then the MIPI organization. We maintain and promote active development of the standards, workshops, plugfests, and seminars, and we're closely involved with these organizations so we understand and know that our solutions meet the specification requirements, so you can have confidence that the tests that we deliver to you with our solutions will meet your needs. So like I said, I'm the USB guy at Agilent, part of the USB-IF Compliance Committee, where we discuss compliance test problems as they evolve and are uncovered in deployment of real products. and also involved closely with the USB 3.0 electrical test spec working group, where we're changing the test specification to meet requirements as they become known. Rick Eads is a PCI SIG board member, is also in Colorado Springs on the Scopes team. Min-Jae Chong is our SATA, SAS, and MIPI representative. Brian Fetz handles the display technology, and he's a VISA board member. And Perry Keller is a JEDEC board member for the memory standards. Like I said, we engage at the highest levels of these organizations to ensure that we understand the testing requirements and help contribute to the specs to make sure things that are defined or placed into specifications are testable. So now let's go on to the USB IF update. So the USB Implementers Forum owns all the standards associated with USB technology, starting with USB 3.0, but going back to USB 2.0 and other older specs like USB 1.1. Within the test or within the USB IF, there is the highest level is the board members. They ratify and approve any specs developed with the subcommittees that are below them, primarily Intel, but NEC, HP, Microsoft, ST Ericsson, and LSI are also board members. Below those are working groups, device working group being the largest. They develop side specs like USB on the go. We just wrapped up work on the SuperSpeed intercept spec, if you've heard of that, underneath the device working group. We expect that to be posted 1.0 in June. And then once the specs are complete, the test specs and the test procedures are developed within the test spec working groups associated for those standards, and then the test procedures will be developed based on those test specification requirements. Once those are both approved, then test houses and workshops can implement those tests and do certification of the different standard requirements. So now let's talk about USB 3 ecosystem and market adoption. As you're probably aware, USB 3 has been out for over 2 years now with a pretty reasonable growth rate, but largely has been languishing behind where I expected it to be, partly due to integrated chipset support. So 2012 is really the breakout year for USB 3. USB in general is most widely recognized as the most successful interface in the history of the PC. Every PC and most portable and consumer electronics devices include USB technology. It's got a huge install base of over 10 billion units and growing at an astonishing rate of 3 billion units a year. Adoption, as I said, is virtually 100% in PC and peripheral categories. And really, in 2012, we're going to see the adoption rate really take off. We went from roughly 77 million units of USB 3 capable products shipping last year, and that's going to surpass that enormously in 2012 to over 400 million units and double by 2013, mostly due to the fact that Intel is shipping an integrated chipset with Ivy Bridge this year, and Microsoft Windows 8 natively will support USB 3.0. So a common question I get is, what are the certification requirements and where do I find those? So if you go to the USB IF website and click on the SuperSpeed USB link, it will show you the certification requirements and test categories for all of the different compliance and interoperability tests that we run at workshops and test labs. This is the product test matrix that you can find on the USB IF website. And I highlighted the different test categories to help you understand what equipment and test requirements might exist for these different categories. So the red boxes indicate the physical layer test requirements, starting with USB 3.0 electrical. So for hosts, you test for silicon and IP. You test all the test requirements that we have listed. For end products, the test requirements are the same. Same thing with devices. And then with hubs, upstream and downstream ports also have to be tested for full compliance to get certification. One thing not to forget with USB 3.0, a key component of USB success has always been backward compatibility. That means you have to meet all of the electrical test requirements as well as the interop protocol tests and backward compatibility test requirements for protocol and the software tests provided by the USB IF. So the blue boxes indicate where protocol test equipment and USB IF test software like USB compliance verifier, which is USB-CV, Chapter 9 tests, and that kind of testing that is required for certification of end products and silicon. So there are two ways to get your product certified after you run through all the tests in your lab to verify that you meet the requirements. You can either go to a USB-IF workshop, or you can take it to a test lab. We now have over 7 test labs certified to do qualification and certification of USB 3 products, as well as full certification capabilities at USB 3 or USB-IF workshops. So Agilent consistently performs and supports all of the workshops that are held a year. We have typically 5 a year, 4 in the U.S. and 1 overseas, generally in Taiwan. This is a snapshot of the test suites we supported at all the workshops last year and this year. USB 3 Electrical Gold Suite, where all the USB 3.0 physical layer testing and certification is done. We support that with our DSA 91304A and 9130, the 13 gig X series oscilloscopes. And then receive testing is done with our bit error rate tester and our de-emphasis box. In the USB 2 Electrical Gold Suite, as I mentioned, you have to maintain and verify backward compatibility to the 2.0 specification requirements. So we do the full USB 2 physical layer testing as we've done for all USB 2 products for many years. In addition, we also provide protocol testing and decode at workshops. This is mainly to test and debug interop issues in all the other suites. So we have interop, backward compatibility, and you have USB-IF software that you have to run on your devices. And if you fail, the way you debug and verify that you meet the requirement and it's not a host problem is to hook it up with a protocol analyzer and verify that you meet the specification requirements. And then also we provide informational cable testing. Cable testing is not capable, you can't do certification of cable testing at USB-IF workshops just due to insufficient time to run through all the testing that is needed. But we provide the ENA at workshops for debug of cables, connectors, and impedance of devices and hosts at workshops as mainly a debug tool. As I mentioned, you can certify your products at workshops, but also test labs are enabled now for certification of USB 3.0. This shows you a geographic map of the test lab locations and which ones are currently qualified for USB 3.0 certification. So you have NTS based on the West Coast in the U.S. They can do full USB 2 certification as well as USB 3.0 device certification. Testronics in Belgium is approved as well, TTA in Korea, and then 3 sites from Allion and XCal Japan. The other test labs indicated here are only 2.0 today, but as they get the right equipment and the right qualification requirements are met, they will be turned on for USB 3.0 certification as well. So what is different for USB 3.0? I like to start with this slide just to let people understand the test and measurement differences as well as the design challenges that you're going to face as you go from USB 2.0 to 3.0 speed and performance requirements. So USB 2 is 480 megabits per second versus USB 3.0 5 gigabits per second. So that's over 10x performance increase in the signal rate through existing channels and a 3-meter cable. The signaling topology for 2.0 is non-return to zero inverse, half duplex, meaning the same transmitters and receivers on both ends share the twisted pair. So you have a lot of wasted bus latency due to bus turnaround times on the USB 2.0 bus. That was improved with USB 3.0 with a focus on getting the full bandwidth in both directions. It's 8B10B PRBS or pseudo-random binary sequence full simplex, which means you have a dedicated transmit and a dedicated receive path between a host and a device or a hub and a device. USB 2 includes only 4 signals in the conductor and the connectors. So you got D+, D-, power, and ground. USB 3.0 includes those 4 signals for backward compatibility and power, but also adds a transmit twisted pair and a receive twisted pair for an additional 4 SuperSpeed signals. This allows you to maintain backward compatibility for 2.0 devices to function in 3.0 hosts and 3.0 devices to operate at a lower speed in 2.0 hosts. I mentioned the cable was 3 meters for USB 3. Going back to 2.0, the cable max is roughly 5 meters. The power has been increased for USB 3, largely driven by mobile manufacturers and portable drive vendors. They wanted enough power to make a bus-powered peripheral that didn't need an external power supply. So power increased from 500 milliamps max for USB 2.0 to 900 milliamps for USB 3. One additional thing to note, there's a power spec addendum that is under review within the USB-IF that will greatly increase the allowable power provided to peripherals and also allow peripherals to provide power to portable devices that act as hosts, and that we expect that to be out in a couple months. But look for that. It adds a higher level of power for both hosts and devices depending on if they want to support it. Suspend current remains the same between 2.0 and 3.0. Suspend is where the bus is basically shut down for power savings and consumption, with 2.5 milliamps being the maximum. For 2.0, one critical difference going to 3.0 is 2.0 does not allow or support SSC, or spread spectrum clocking. This is a requirement for USB 3.0 SuperSpeed, and it is also one of the challenges that device vendors struggle with to get the implementation of SSC correctly. Also, a significant difference is the test methodology for 2.0 versus 3.0. 2.0 tests the transmitter at the port with minimal loss through a minimum fixture. USB 3.0 provides far-end testing, which I'll describe in a minute. But basically, we test the transmitter as if it passed through the nominal case channel, which includes a PCB trace to emulate either device or host routing on the host or device platform, plus a 3-meter cable. And also, for USB 2, the receiver testing was fairly simple. Didn't do jitter stress analysis of the receiver equalizer. For 3.0, that is a required test for both devices, hosts, and hubs. And we do a full jitter stress test for the receiver jitter tolerance, as well as a closed eye test on the receiver equalizer. As I mentioned, SSC is a requirement for SuperSpeed. Transmitter testing for SuperSpeed is done at the far end, and receiver jitter tolerance is a requirement for USB 3 SuperSpeed. And one more point about that, that is the biggest area that people face difficulty in physical layer test, is passing the receiver jitter tolerance test requirements. So I mentioned transmitter testing for 3.0 compliance testing. So this is performed with the Agilent U7243A transmitter compliance test application. This automates all the required tests for transmitter compliance and verification of USB 3.0 products, hosts, devices, and hubs. I mentioned it's tested at the far end, and we achieve that in the application through an embedding channel function where we emulate a channel loss topology defined by Intel and measured with a network analyzer to create the loss profile of that channel that we apply to the measured waveform directly at the output of the transmitter. So in effect, we're measuring at the connector interface of the device or host under test, but we apply the loss associated with the required channel, which I'll describe in a minute, through the embed function, which you can see selected here for the device. So these embed device transfer functions and host transfer functions are included in the application. So other than selecting device or host or hub, you really don't need to worry about what that transfer function does or how to apply it. It's automatically included in the application. The transmitter tests include low-frequency periodic signaling tests, LFPS. You can see those in the Select Test tab below the main setup window. And then SSC is automatically tested as well. This is a required portion of USB 3.0 transmitter design. One thing to note, a lot of early silicon had the option to turn SSC off. This is still allowed due to a backward compatibility problem with early hosts that shipped that had a problem with proper implementation of SSC. So I always recommend designers to include the mechanism to turn SSC off. It's required for certification testing to verify that you meet the requirements when it is turned on, but people are allowed to turn that off to solve this interoperability problem with hosts that had center spread SSC. SSC on USB 3.0 products is required to be downspread. What that means is your signal rate of 5 gigabits per second is downspread or modulated down to a lower data rate using a triangular profile waveform to lower the EMI emissions at that frequency. Transmitter testing for certification is done at the far end. I mentioned as we implement that through the embed function, and then we test the I pattern, transmitter jitter, and the amplitude of the signal as it would appear at the end of the channel after a reference equalizer is applied. So one additional thing to mention about transmitter I pattern testing is that it requires 2 different test modes to be supported by the product under test. The way to get into those test modes is quite a bit different than what USB 2.0 requires. USB 2.0 requires a special tool developed and provided by the USB-IF to enumerate the device or run on the host under test, and you drive the software to indicate the test modes that you want to enter on the device to test the signal quality requirements. For USB 3.0, you don't require external PC-based software to run the test tools and put the device into the proper test modes, which is a big improvement for testability, particularly for mobile or embedded environments that don't support Windows operating system, which the tool requires. So for 3.0, all devices start up in a polling state, and they're looking for low impedance termination on their transmitter to indicate they're connected to a real receiver. If they detect that, they enter the polling.lfps mode shown here, which is one of the first things we test for transmitter compliance. If the device and host do not complete the LFPS handshake or low frequency periodic signaling handshake, then they time out and go to compliance mode. The first compliance mode that devices default to or hosts is CP0, compliance pattern 0. It's effectively a D0.0 scrambled or electrical idle pattern. It's a pseudo-random pattern that is basically indicative of nominal worst case signaling pattern for transmitter testing. The second pattern required is CP1, which is a clock pattern, D10.2. And we use that to get a more accurate measurement of random jitter, which is hard to achieve with a very long non-repeating pattern like CP0. So we take the result of the random jitter measurement, feed it into the test application software, and then measure deterministic jitter and total jitter using the SIGTest integrated tool. SIGTest is a software tool provided by the USB-IF that we integrate directly into our test software to do official compliance testing. The way you go between CP0 and CP1 is through what's called a ping LFPS signal, where we toggle the compliance mode by issuing a signal into the receiver of the device under test, and when it sees that signal, it will transmit or toggle to the next test pattern. So as I mentioned, transmitter test requirements are far end for USB 3.0. What that means is the eye is very close. So here we have the minimum eye height requirement for USB 3.0 transmitter testing. It's 100 millivolts peak-to-peak eye height. This is actually after a reference equalizer is applied by the software. So we're running through a very long channel. In the case of a device, it's 11 inches of trace and a 3-meter cable. And the eye is effectively closed. Then you run the CTLE, or continuous time linear equalizer, transfer function defined by the USB-IF and included in the tool to analyze the eye as it would appear in the receiver at the far end of the channel. So this connection diagram shows you the effective measurement topology for USB 3.0 transmitter compliance. So we have the device under test, we have the emulated reference cable, 3-meter cable, the reference test channel, which varies between host and device, and we would effectively be measuring the I at this point into the scope after the CTLE reference equalizer is applied. Receiver testing runs through the same channel topology, but is quite a bit different in the mechanisms to get into the test modes. So the main mechanism you need to support and be able to get into to support receiver testing is loopback mode. So loopback is a condition of a device transceiver state where every pattern sent into the device receiver will be sent back out the transmitter. We utilize loopback by initiating the handshaking through the bit error rate tester, starting with the RX detect like I described for transmitters, but instead of timing out and going to compliance pattern, you see here's a scope capture of the initial sequences of the host Jaybird handshake. So those short bursty pulses are low frequency periodic signaling handshakes. When the device under test, shown in orange, sees the LFPS burst being sent by the Jaybird, it will transition to the next sequence in the link training state machine, which is TSEQ, or transmitter equalization pattern. Once the Jaybird goes to that pattern, the device sees that and responds with the same. And you can see up here we go RX detect, where they detect the low impedance of the receiver, polling.lfps, which is the bursty pattern I just described, the RX equalization polling pattern, or TSEQ, which is shown here. And then once both sides adjust their equalizer for a sufficient amount of time, then you start sending training sequence 1, training sequence 2, with a loopback bit set in training sequence 2, which is an indication to a device host or hub transceiver to go into loopback mode. And once it's in loopback, we begin the testing of the receiver by adding jitter components at the required levels to make sure the receiver passes without any errors. And this is an example test report of receiver compliance testing and jitter tolerance as run at a USB workshop. The green line indicates the test requirements in the spec, and the dots indicate the test points for compliance of the different sinusoidal jitter amplitude requirements. This corner frequency is 4.9 megahertz. You can see as we go down in frequency, the amplitude that your receiver has to withstand of sinusoidal jitter increases. So you have roughly 2 UI of jitter added at 500 kilohertz, and the receiver has to pass with no more than 1 bit error at that test point. And then at 4.9 to 50 megahertz, we had a 20 milli UI of jitter to the receiver with an underlay of consistent amount of RJ at all those test points. On the right, I show the results of a jitter tolerance test. That's not a compliance test requirement, but we run that at all compliance workshops to give the designer an indication of how much receiver jitter test margin they have. In this case, the limitation of the equipment is shown by the green dots, and when we start seeing bit errors in the loopback mode, we show a red dot indicating where we started seeing failures. You see the lowest point that the receiver can tolerate is usually between 10 and 33 megahertz of sinusoidal jitter, and that's a pretty common weakness of all receivers. And in this case, this device has a fair amount of margin, even at the worst case jitter tolerance test points. I mentioned compliance channels. There are 2 compliance channels currently defined for host and device testing. The host channel is 11 inches of trace as defined by this topology. There's a white paper on the USBIF website. So 11 inches of trace means from the A connector to the host package, it's nominally 11 inches of trace in our compliance channel model. Then 3 meters of cable for both device and host, and then the host trace budget is approximately 5 inches of trace. So the total channel end-to-end from host package to device package is 11 inches of host trace, 3 meters of cable, and 5 inches of device trace. Now, depending on whether you're testing a device or a host, you will use the appropriate pieces to emulate the worst case channel to get to the other end of the channel and test at the receiver. One thing that's in progress right now is definition of a short compliance channel. That's to emulate the connection topology where you would plug a flash drive into the host port here and only run through a short USB or a short USB 3 trace to the host package, as if the chip was implemented close to the connector, which is common in a lot of laptops today. So the short channel definition currently being defined is no cable and short PCB traces on both devices and host. That's important to test and implement due to the fact that one common product for USB 3.0 now is the flash drive, which has no cable. So we want to make sure that the receiver equalizer functions correctly when it has almost no loss in the channel. So I mentioned host and device compliance channels are different in that when you test a host, you want to add the compliance channel to emulate what a device would appear to add to the signal for the transmitter and receiver under test. So you add 3 meters of cable and 5 inches of trace when testing a host for transmit and receive. And this is the fixture set provided by the USBIF for host testing. It adds 5 inches of host PCB, a 3-meter cable, a breakout board to give you a short path back to the error detector on the Jaybird, and this is the fixture used to calibrate the eye for receiver testing. For device receiver tests, you get the other end of the channel. So you get the 3-meter cable, which is the common piece, and then you add 11 inches of trace to emulate the loss that you would see through a typical channel connected up to a host to emulate this transmitter and receiver eye opening at the host receiver. This shows you the physical connection topology using our bit error rate tester. So you send the signal, the stress jitter pattern, into the device test fixture, 3-meter cable, the breakout board. You get the device in the loopback, and the loopback signal feeds into our error detector, and we verify that the pattern we send matches the pattern that you return to check for bit error rate at each jitter tolerance frequency and the closed eye topology. So I mentioned physical layer compliance pitfalls. Here's a common list of key issues that people tend to face when they go to a compliance workshop or test lab or certification in their own facility. So I mentioned transmitter spread spectrum clocking is an issue. Basically, you can have incorrectly formed or improperly formed SSC profile. So here's a compliant spread spectrum profile. The Jaybird has a unique capability to add intentional stress and distortion on the SSC to make sure the device can handle it. And this is an example of a capture of a noisy, non-deterministic SSC profile that we see on some early products. Receiver testing, I mentioned, is the biggest problem for most developers after they get their device up and running. First of all, it's challenging for some products to get into loopback. If you can't get into loopback, you can't test the receiver. We can, assuming we can get the device into loopback, we can test the receiver. I haven't run into a piece of silicon yet that I can't get into loopback, but sometimes it's challenging because it takes different numbers of different handshakes for the different sequences I described earlier. The calibration issues is not really a device problem. It's more of a test and measurement issue. Agilent has the most accurate and repeatable calibration software in the industry today using the N5990A Midify automated calibration software. But this is a recurring problem for me at workshops due to the fact that my competitors do not have automated cal implemented fully to make sure the calibration is consistent and accurate to give you repeatable results, both run to run, lab to lab, as well as from one test suite to another. Improperly formed and inaccurate de-emphasis is probably the biggest cause of eye failure for transmitter testing. It's also a problem on receive testing if your device, your test solution doesn't have properly formed and clean de-emphasis. This shows you what the test requirements are for the spec, and this is an example of non-compliant pre-emphasis implemented by a poorly designed transmitter source. And then receiver jitter tolerance failures. I mentioned most devices have weaknesses at 10, 20, 33 megahertz, partly because that's where their reference clock is designed, and their PLL is designed to amplify that frequency. So those are important areas to test when you're verifying your design. And then last thing to mention is protocol decode on a scope. We have implemented protocol decode on a real-time scope for 2 years now, and USB 3.0 is one of those applications. It's a really valuable debug tool for receiver testing to verify the device state is what you think it should be during the sequence of the handshakes to get into loopback. But it's also useful for the last bit of debug between PHY and logical layer problems. You can verify that the signal integrity of your packet looks good, even if the decode is wrong, and then kind of determine whether it's a logical error or a physical layer problem using the protocol decode. It doesn't replace a full protocol analyzer for software firmware development and full application decode, because the scope record is limited, so you can only get a snapshot in time of what's going on in the bus, but it's a very valuable tool to isolate digital versus physical layer problems. And then the last thing I'll mention is not USB 3 specific, but it's a common question I get about high-speed interchip test solutions. So high-speed interchip is a sub-spec to the USB 2.0 spec. Basically, it's a chip-to-chip topology. I mentioned we have just released, or will release in next month, the SuperSpeed interchip, which achieves the same thing with the higher performance requirements for SuperSpeed PHYs. But basically, it provides a chip-to-chip interface that's low latency, low power, and you can get the specification from the USBIF website here. Agilent provides both a serial decode software package on our scopes and a compliance application to test the electrical parameters of those signals. Now I'd like to turn it over to Don. He's the USB product manager for Digital Debug Solutions, and he will discuss protocol and logic analysis solutions for USB 3.0.
Hello, everybody. I just want to say thank you for attending here and watching this presentation. I want to follow on with Jim's presentation of all of the information at the physical layer, of all the testing that needs to be done there, is getting the bits successfully passed back and forth. Now we start moving up and getting the full communication going on between the two end devices, and there's a whole series of different protocols. It's not just one protocol that has been defined by USB 3.0 for operation, but a whole series. And in this diagram here, you can see a listing of some of the different protocol specifications of how you do packet delimiters, how you do notifications, what constitutes a transaction in here at the protocol level. But then you also need to be able to move on into the device drivers of how that communication pipe between the host and the device actually occurs. And there's going to be hubs in between that are capturing the signal and then regenerating the packets on the other side and sending that information back and forth. The protocol analysis gets you into the detail of all these different layers and bring that entire picture together of what's happening here. Some of the common types of problems that occur that you need a protocol analyzer for really relate to that stacked model of what the USB IF is defined in this specification. At the host level, doing the device drivers, there's testing the driver compatibility. With 3.0, it's really been custom development so far, but with Windows 8, it's now going to be integrated into the operating system itself. And so there's still going to be compatibility issues of how do the devices interact and testing all the way across. And if there's a timeout problem, how do you detect those errors? Lots and lots of custom extensions occur within the device drivers. You need to be able to do some custom development in your protocol decode and being able to pull out the pieces of information and analyze what is occurring within that communication link at the highest level, assuming that everything else below it is successfully operating. And then there's full custom devices that are unique, not standard in the industry, and how you can be testing those and developing the device drivers. You need to be able to look at all that different information. Often when you're looking at this high level at the pipes of the communication between a host and device, you need to be able to capture long periods of data. There's lots of intermittent type problems that as Jim mentioned of with oscilloscope, it can do a decode, but it has a very, very limited view. Now, you may need to be able to look much, much deeper when you're looking at the device drivers and getting into the detail of that. So lots of different challenges in that. How do you set up the filters to capture the information that you actually need in that operation? Then you can move on down. There's a whole test specification around the link level and the protocol and error recovery that's available from the USB-IF. How do you handle the buffer management between the host and the hub? Because there's defined by the specification 4 buffers will be available, and every time a packet is received, when buffers are available to receive the next packet, there's a whole communication process between the end devices that's usually handled in the firmware or in the silicon loaded into the device itself, but that process has to be handled quickly and efficiently. And you need to be able to test for those and detect if there's an error, because that can throw a link completely out of whack. You also need to be able to look at when things happen at the low level. What's going on at the operations here for communication, of if there's an encoding error, or if there's the LFPS signals are not happening in the right timing frame. Being able to capture all that and synchronize all that information together into one communication and see the entire process for what's happening there. When you're looking at USB, as Jim said, there's the 2.0 specification and 3.0, and there's some significant differences. But on a given link, you have the 2.0 communication channels, but you also have the 3.0 full duplex or full simplex, full unidirectional communication going on at the same time across that link. And any device that plugs in out here, if they plug in at 5 gigabits per second, the SuperSpeed, if they're not able to successfully lock up at the 5 gigabit speed, they drop down automatically to the 2.0 speeds. If you're using hubs in there, you may have a combination of both 2.0 and 3.0 communication over that same cable that you need to communicate and compare those operations in real time and capture that information. Just as a quick example of that, I've got a picture here here's an analyzer connected up on a USB link between a device under test that's connecting through a hub, going into a host operating at the USB speeds, and it may change speeds. One device is communicating at 3.0, another device is communicating at 2.0 speeds at the same time over that link. So you need to be able to handle not only the different speed challenges that occur of all the way from 1.5 megabits per second to 3 gigabits per second on that link, but handling the different protocols of where there's in 2.0 that there's some protocol changes that occur of everything's a polling operation in 2.0 of a token, data, and then a handshake back for successful data transmission, whereas 3.0 with those 2 unidirectional links, now you can have just data and handshake. As Jim said, with the 2 unidirectional links, you have much more efficient use and throughput operation in not having to turn that link around back and forth. In just the operation here of token data handshake, you've had to turn that link around twice for operation, whereas it's continuous flow of information with 3.0, and you need to be able to capture that information and the protocol differences that occur. Now, while you're doing that low-level thing, is just looking at the higher level, at the device channel, you're still doing, for example, SCSI writes to a disk drive. So here is a communication at a USB 3.0 speed. The channel is 3.0. It transmitted 65 kbytes of data across the link, but the very next piece of information in here is on a 2.0 channel, and it's also transmitting 65 kbytes of data. So at the device level, at that pipe, the communication is the same, but all the low-level processes that occur to support that operation are captured underneath this, and you'd have to expand, you'd do a simple expansion to see all the packets. for 65,000 bytes, that there's at least 128 packets that occurred underneath this communication link. And all of that information is captured and stored in there, and there's any piece of that that may be corrupted that you need to be analyzing and occurring what's happening. Very different USB protocol operations, but the transactions are the same. While you're doing that, you also need to be able to look at how's the lockup sequence occurring. So in this particular diagram here, I'm showing you to bring the link up, you start off with LFPS signaling, the low frequency signaling. In a display mode, you want to be able to see of how long did that information occur. This histogram mode displays a time period of when did things start, and then when did we transition into sending ordered data across the link. And in that transition, there were some errors on the link, then link management traffic that occurred. Then there was another significant period of time of just doing all the training sequence, the order sets, or the training sequence of getting all the receivers synchronized on. Critical time for some of the scope operations and seeing that. But once you get past that, then the data starts flowing. And that data starts comprising into all of your reads and writes. There's lots of other steps that occur in there about device enumeration and signaling speeds and negotiation that goes on. But all of that needs to be captured in so you can see the entire flow of what's the timing of information, how does information synchronize and lock up to get into the right points for communication in this operation. While you're doing that, you also need to be able to check if any problem may lead you back to the low level of what were the 10-bit codes that were occurring across that link, and being able to display of exactly here's the bit sequence that was sent across the link. Even if it is errored, being able to capture in of what the heck happened here, or trigger on those events and look at repeating sequences, or trigger out to an oscilloscope or other types of devices to see exactly what's going on, trigger into your firmware tracing of what's happening there. Jim showed you a diagram of with the receiver testing of putting it into these different tests of this operation of getting into the loopback mode. The specification has this linked training state machine that uses a bubble chart to show of, okay, from an inactive state, you go through receiver detect, and then after you detect the receiver, you go into the polling sequence to get the training or the low frequency training, and then you go through the training sequence itself until you're finally into the U1 operations. Well, you need to be able to look at that information. He was showing you one view of what it looks like on an oscilloscope of all those different pulses, and then it goes into TS1. When you look on a protocol analyzer, you need to be able to see those pulses of starting the low frequency signal goes out, and then the end. And so here's this pulse. It was a 1 microsecond pulse, well within the specifications, and being able to make the measurements there of exactly what's going on. Also being able to see the overall sequence of from the host to the device. When did the device start responding to those pulses and sending the return signal to begin the training sequences and bringing up that information and showing exactly what's going on. There's also important aspects of being able to look at the flow control. That's moving up that protocol stack to look at how do I recognize buffer credits. That's handled more by the firmware within the device. So you can see in this type of information, this training sequence, here's the TS2 commands being sent. As soon as the TS2 completes, there's a link good 7 sent by both sides, and then they both send link credits for the 4 buffers that each side of the link has to maintain. And every time there's a packet sent, the other side responds with, okay, I've got that information, use the next buffer. And two packets went out over here, and the responses came back of, okay, link good on 0, link good 1, and then the credit sequences occur. And you need to be able to monitor that. If there's an error at any one of these levels, can throw your complete link out of operation. A good protocol analyzer will highlight those events and automatically lead you to that error process. This is just more of going into that. Here's a data packet. A data packet goes across the link. It's a GET descriptor. At the higher levels, so remember our different sequences, there's the data transaction, and the transaction comes back with an acknowledgement here, but the link level is still doing its acknowledgments of receiving that packet. So there's this whole timing sequence of it has to process it through the buffer first before it sends the acknowledgement back from the other end. And that information flowing back and forth across that link and being able to see all that information. Power management, as Jim said, that's a key thing of what USB 3.0 brings to the table, of being able to see when a device goes into one of the low power states, of either by packets or by timeouts. Here's just a list of some of the different commands that we can trigger on. You can look at actual transactions, but it's also important to be able to look at timing of events. For example, for U2, it's based upon a timer exceeding 256 microseconds. So even though the device went into link go into state U1 and the host acknowledgement, then there's electrical idle, then that signal came back of low frequency signaling. You need to be able to measure that of what was that time difference, 392 microseconds. At that point, you know the device should have gone into state U2 of a low power state. Going back to tracing through your device development and making sure that it's operating, getting that signal out is an important part of the testing process too. And that's why the synchronizing between different devices is so critical. So whether you're synchronizing from a trace program in your software, or you're tracing to an oscilloscope, being able to get a trigger out to signal of, okay, this is the event I'm looking for in this operation. And so that signaling operation of triggering on a timeout type of event is some of the things you want to be able to do with a protocol analyzer, and that is some of the areas you need to be able to look into. Significant periods of time that occur in the operation. It's also important to be able to use complex types of operation if you're looking for specific types of data. Here's a link of monitoring write commands from using the process of the USB attached SCSI protocol, which is the new mass store specification. Well, there are actually 5 pipes that are set up in that communication, and you may only be concerned about one of them. So in this link here, we're looking at, here's one communication, data going out from the host to the device, and we can see it's address 1, pipe endpoint 2, so there's one pipe, and then all one's in the middle is probably the information we're looking for, something that's hidden in the middle of a large transaction of here's in data from on endpoint 5. We can also see that there was another endpoint involved with data flowing out and across. So there's different pieces of information you need to correlate to and to find your operations and see the timing of events of when device is not ready and how long does it take the device to respond when it's ready to receive more information. So finding intermittent problems, you really need some complex trigger conditions at times. You need to be able to closely control your filtering capability because of the depth of information. Sometimes your traces can take days of information to look for these intermittent problems. And so you need to be able to capture and turn filtering and capturing on and off as needed. I want to mention too about some of the error insertion capabilities that will be needed for testing a protocol. Quickly before I do that, I have a couple slides here. There's lots of different device classes, many standard, but there's lots of capability for vendor-specific type of capability. And USB defines codes for each one of these, and there's D codes available for these different types of device classes in your operation. One specific one I just want to mention is mass storage protocol. USB, when they came out with version 1.1, they also released a mass storage protocol called bulk-only transport. And it supported full-speed operation and low speed. It was pretty slow, the throughput was similar to a parallel port. When 2.0 came about, this specification, the bulk-only transport, was still sufficient to meet the needs of 480 megabit throughput. But now that 3.0 specification has been released, USB is no longer a bottleneck, and they needed a faster protocol operation. They released the USB attached SCSI, a whole other device class that supports advanced queuing operations to take multiple SCSI commands and operate that to a device. It gets you much better throughput. And there's always going to be new device classes being developed constantly. Active testing, you need to be able to do some active testing. There's different ways to do that with a golden device of some device that you trust. Does it work in the generic operation? But then you need to be able to take that golden device and insert errors. And that's one of the common areas that's greatly needed to verify a device operation. Some of the key benefits are being able to do error injection of common errors, even a 10-bit error, or scenario testing, testing a performance problem across a link of what if a link credit is missing, and also problem replication of errors. So active testing, as you go through these, Command A goes through the device, and we can change it to something totally different as it flows through that communication. Testing a device driver can be an extremely good operation, and here's a quick example of how we do that. We're using an analyzer to capture the data, the jammer to modify it, but what we're doing is we're waiting for a read command, a SCSI read command, and then modifying that packet in real time as it flows through, and being able to test the device operation. In this case, we're modifying the DTO and FUA bits to be able to change cache operations in a mass storage device. So just some of the different examples of being able to do 10-bit errors. You can inject alignment errors into a link. You can inject link credit types of problems into a link, forcing incorrect buffer sequencing to test a device, or also modifying into device classes for operation. So with that, I know I've reached the end of my period in here. I want to turn this back over to Jim for some wrap-up.
Well, thank you, Don. So this is just a summary of Agilent's test portfolio for USB 3. We have the total solution package for all your test and verification needs for USB 3.0 compliance and certification testing and debug. Starting on the left, we have a full portfolio of transmitter test solutions supported by all of our 12 gigabit and higher gigahertz and higher oscilloscopes with our protocol analysis software, as well as our USB compliance test software, and our Agilent U7242A USB 3.0 test fixture. Interconnect test, which I didn't discuss, but we have full cable connector certification based on our network analyzer with option TDR. You can do full cable characterization and compliance testing in 15 minutes with this test setup using the test fixture shown here from Bitify. And for receiver test, it's based on our high-performance serial bit error rate tester and our de-emphasis box to generate the required full bit de-emphasis. And you need the USB 3 ET test fixtures provided by the USB IF to provide the compliance channel test stress conditions for receiver testing. And then you loop that back to the error detector and the JBERT to do the bit error rate testing. Automation is covered for receiver test and calibration using the Bitify software shown at the top. The N5990A automatic test software does full jitter tolerance as well as receiver calibration tests. And then, as Don mentioned, we have a full set of protocol test suite solutions with our analyzer software package, the Mako analyzer, and then the jammer product to introduce errors and do fault detection and error generation and response testing. As I mentioned before, USB 2 or 3 is projected to grow significantly in 2012. I believe it's the breakout year for USB 3. By the end of 2011, we had 8 companies certified 3.0 host controllers: AMD, Media, E-Tron, Fresco Logic, Intel, Renesas, TI, and VIA Labs. So that's a lot of host controllers. But the key is that Intel is launching Ivy Bridge with direct chipset support for USB 3.0. That was announced April of this year. The Panther Point chipset designed for Ivy Bridge is what includes the native USB 3 support, and not least of which Microsoft Windows 8 will support USB 3.0 as well. So in summary, things to remember. Intel is launching Ivy Bridge this year, so it will be 100% penetration into the system market starting this year and next year in force. With Windows 8 support, you get native support for host and like mass storage class drivers for devices and hosts. Agilent has the industry's only complete USB test solution portfolio, including all the physical layer test requirements for transmitters, receivers, cable connector certification, as well as a protocol analysis tool set. Our transmitter receiver solution is the worldwide market leader today for USB 3 product developers. Our Agilent protocol analysis and error insertion jammer enables the complete testing required for design confidence, because the typical test conditions that you need to generate to make sure your device and your software and your firmware all meet the requirements, you can't achieve that just with a selection of peripherals that are already on the market today. Agilent USB solutions, as I mentioned, is adopted by test labs worldwide, so you can get confidence that when you go for certification at workshops or test labs, that they will be testing with the same equipment that we described here today. Confidence in our solution comes from maintaining a leadership and participation in standards bodies, so we can ensure that our test solutions meet the current requirements and test to the specification certification requirements. All right, well, thank you. That's the end of our presentation. And I will open it up for Q&A.
Thank you, Jim and Don. So this is the time for questions. If somebody has any questions, so please write it on the Q&A session on the WebEx. Jim, can you please repeat on the question that people asked so far and the answers?
Sure. We started off with a question on what are the benefits of getting products certified to the USBIF and what are the requirements to do that. There are 2 benefits to getting certification. First is that you get it listed on the USBIF integrators list that's accessible by USBIF members. It's basically a list of every certified piece of silicon and end product that gets certified on this list. OEMs use this to select silicon that they want to integrate into their product, knowing that this implementation as submitted to the IF passed all the requirements, and it's a great screening tool to start your search for products that you know can get certified if you implement them correctly. To get it certified, you bring it to a workshop or a test lab. If you pass all the testing requirements and fill out the checklist requirements and that kind of thing, then you will get certification by the USBIF. And it allows you to use the official certified USB 2 or USB 3 logo on your product packaging and literature. The next question was about Thunderbolt. I get that a lot these days. People are asking, is Thunderbolt going to replace USB? Does it compete? How does that affect my choice on going with USB 3 in the future? My perspective, and a lot of the industry feels the same way nowadays, is that they're not mutually exclusive. Most systems, in fact all systems that I've tested so far for Thunderbolt, have USB 2 today and are migrating to USB 3. They're complementary in that they coexist and solve different problems. Thunderbolt is a very fast connection, but it's limited on the capabilities that you can connect to. You can only daisy chain up to 7 products, and they're higher cost, higher power devices, typically RAID arrays or large storage devices. USB 3 gives you the bandwidth that you need for most existing technologies, but it's much more portable, much lower cost. And they're both supported with Intel's Ivy Bridge chipset. So for the foreseeable future, I see both Thunderbolt and USB 3 coexisting on systems, but USB 3 by far is going to ship in much larger volumes because it's backward compatible to USB 2, which is in every platform today. Next question was, what are the scope bandwidth requirements for USB 3? It's similar to PCI Express Gen 2 signal rates. Well, it's exactly the same, and the minimum scope bandwidth for that is 12 gigahertz. And I'll turn it over to Don. The next one is a protocol analysis question.
Okay. The next question was how much buffer is required for doing protocol analysis. It's one of those questions that goes back to it depends. It depends on what you need to capture, what you're looking for. But kind of a rule of thumb, if you're working with SuperSpeed data traffic, you're talking about two 5 gigabit links that you're capturing all the data on if you need to be able to look at all the bits and bytes going across the link. And you can fill up about a gigabyte of data buffer in a second in that kind of operation. So it's really important to have large capture buffers be able to have any significant period of time. Now, by using filters and triggers in a very intelligent way, you can optimize the use of that operation, but you have to really know what you're looking for. So when you think of capturing that time frame of information, 1 second or 2 seconds usually isn't enough time period to be able to look for all the different situations you're looking for. So really you need to have more like around 9 gigabytes or maybe even more for your capture buffer as a general purpose when you're doing super speed operations. But you can get by with smaller, but you have to be much more careful about the way you utilize the system. There was another question too about what kind of controls the jammer has, because I mentioned about it can do error insertion and modify packets. And can it control the V-bus? And yes, it can control the power bus across the USB link of turning it off and on, and not controlling the power levels, but controlling is it on, is it off, and turning that off. And common usage would be for testing some power dropouts of say 100 milliseconds, take power away, and then turn it back on and see if the device, what happens to the device for that time period, and modify that dropout for different periods. At what point does it have a problem? At the same time, the analyzer is always measuring the amount of current and power being drawn, so you're getting a clear display of what the device usage at any point in time across that link is. And that's all the questions we have right now, unless somebody else wants to post a question. I do believe we're wrapping up here.
And one more question.
Okay.
I think I can take this one. So the question is that compared with the protocol analyzer, what's the limitation of scope analog capture plus USB decoding and protocol display? So you got to remember real-time scope is sampling for USB 3 at 40 gigasamples per second. So we may have 1 gig or 2 gig record on a scope, but that's at very high sample rate. So we're really limiting the amount of time we can look at with a scope protocol analysis capture. So the difference is how much time we can capture. So USB 3, for typical sample rate that we use for the protocol analysis tool, we're looking at maybe 2 seconds maximum of bus protocol activity. When you're looking at large data transfers or enumeration sequences, those can last for seconds, and problems that exist in firmware or software can sometimes be only apparent in days or hours of record or transaction captures. So Protocol Analyzer is the tool you need to verify your firmware and software meet all the requirements for multi-link connections. The protocol capture and decoding on a scope is a complementary technology that can be used to isolate. When you find the error, you do cross-triggering with the Protocol Analyzer to capture what's going on the bus with the scope, and then you can verify that it isn't a PHY problem that's causing this, that it's actually a firmware or software or digital problem.
The one additional thing I'd mention on that as well is all of the device classes, is getting into the higher levels, restitching together a transaction for operation is something that's not part of the scope operation. You really need a protocol analyzer that starts looking into the operations in there, buffer credits that are going back and forth, of detecting if there's an error in that process. That's where the protocol analyzer starts following the state of the information and stitching information back together and showing reads and writes at the higher levels versus the USB protocol itself.
Okay, John, Jim, thank you so much for this. I think we can wrap this up. You will see an evaluation form pop up in your screen. We will appreciate your feedback. Thank you all for joining, and we can close this session.
Thank you all.